Hi, so my talk is named, like you can see it, of course, Parsing Rust code considered harmful. My goal is to show the different ways that allow a Rust station to perform static analysis of Rust code. I won't go into the actual algorithms because I'm bad at algorithms. I will show how the different tools available in the Rust community can be used and leveraged in order to make static analysis easy. So, I'm Sasha Pourcelot, as it can be said. My pronouns are she and her. And basically, you can ping me everywhere on the handle Scrapcha. I'm a computer science student at Polytechnique Sofia, which is a French school and nothing much to say. I will graduate in September, which is so great. I can't wait. When I'm not studying, I'm working as a software engineer in a French company whose name is Trustinsoft. Basically, my role is to build a POSIX-compliant implementation of the file system manipulation functions, which we can use later for static analysis. Our goal is to be able to find every possible source of undefined behavior in a C program. And this is the most awesome jump ever. Anyway, and I also have done a few contributions to the Rust ecosystems, including the compiler itself. I did various pull requests, and I also worked in the Tremor project in the spring. So let's start with the basic, static analysis. The whole point of static analysis is finding a property. It can be literally anything, literally anything about a program, but without actually running it. And this is where the magic happens. You are not allowed to run something. You can't just look at the code and deduce properties. The most simple example, which we all know, is type checking, which means that you are looking at the program and basically finding potential type errors before compiling the program so that they just can't happen at runtime. You also have dead code path detection, which is a lint which is quite common in Rust. There are also basically every kind of lint, such as unused variant or attributes. And what I will talk about today, mostly breaking change detection. So basically, this whole talk will be about how I developed the project Cargo Breaking from last summer up to this summer. So Cargo Breaking is a tool which aims to flag potential sources of breaking change in a Rust crate. The goal is to flag a breaking change before a release happens, so that we don't have to break code on the library user side. The end goal was to embed it in CI so that every pull request that is opened by a Rust station immediately gets checked against breaking changes, which would be great. And the role for the whole community could benefit it by getting more insurance that updating a crate, like running cargo update, is just safe and cannot fail in any way. So there are a lot of sources of breaking change. The easiest one, which I showed here, is to flag differences in the public API. For instance, here I added a specific mood parameter, which basically makes previous calls to the function night name just invalid, because you can't run a function which has 2 arguments if you only give it 1 argument. So in this very concrete example, night name has a new parameter. It is a breaking change, so it must result in proper semantic versioning upgrade. This is not always that easy. Basically, there are so much ways in making. There are so much ways to make a breaking change which is almost unnoticeable. For instance, adding a second as-ref implementation to a type can basically destroy everything, because the trait method resolution works well when there's one candidate, and it just bails when there are more than one candidate. Also, we have a way for now to add custom variants to enums thanks to the non-exhaustive attributes. We also can add fields to structs, which is very great, and this is something we must take into account when dealing with breaking changes. It's also kind of easy to accidentally remove the send and sync traits of a type by adding like a member or something which is not itself send or sync, and which is even more weird, changing the size of a type if you are doing some extra magic could trigger breaking changes, especially if you are trying to run transmute on it, because changing the size make transmute just stop working. And I spent a lot of time figuring out various ways to just various reasons for a program, for a library to break. So I'm sorry, this is the crime we are all doing today. We are not going to deal with anything stable. We will try to use stable tools, but it is mostly likely to stay unstable for a while. There are some discussions from people who are very interested in making all the tools I'm talking about stable, but it's not something available for now. In the worst case, we can still use the Rust bootstrap environment variable, which allows us to cheat and use nightly features when not actually running nightly. It is a crime. It is a crime we are all willing to commit today. So, when dealing with breaking changes, we have to find information about the crates. What are the functions? What are the traits? What are the types which are defined? All these things are called the items. This is the official name of anything you can find in a module. So, how do we get information about a crate? My first approach was to just use a very simple parser. So basically, it was about I wanted to read a file and just give its content, so a string, to a parser, which gives me a very nice syntax tree about what's in it. And perhaps we may figure out a way to actually perform analysis on it. So I needed a parser which was able to parse the whole Rust syntax. And actually, this is the moment I discovered the scene crate. Scene is a treasure on its own. I could give 3 different talks about scene. It has so much nice properties which are clearly undervalued. Anyways, so scene can parse a string and give you a syntax tree corresponding to it. And this is like perhaps the easiest way to get the syntax tree of a Rust crate, because it's literally pulling a dependency which is already here, because scene is everywhere. And it just works, which is incredible. But this approach is not perfect because you cannot handle macros. It would mean that you can't, like, figuring out a way to expand macros on our own is just too complex. This is just too much work. So a solution, a way to avoid this issue is instead to run cargo expand, get its output, and just feed it into scene so that we have proc macro expanded code. This is supposed to be another crime because we have a very useful mechanism in Rust which prevents variables defined in macros to be referenced from the outside in this way or the other, which is called hygiene. So this is supposed to be a crime, but luckily for us, hygiene doesn't apply at the item level. It only applies inside a function body, so we're all clear. This solution is very stable, actually. It's like if a new kind of syntax is ever add it to Rust, then I just have to bump a dependency, literally just scene, update scene, release a new version, and it will work. Especially, this is actually not even required because scene has very nice fallback modes where if it detects something it can't parse at the item level, then it will just stop and give the whole tokens that as if it failed to parse, actually. And nothing can ever break in this way. The problem is that this cannot be that simple. For instance, we are just dealing with tokens, with identifiers, while it will be way more useful to have every import resolved, because this way we don't have to write a complex import resolver on our own. Similarly, there is no support for dependencies. If I have an item in my API, for instance, in function, which returns something that comes from another crate, then from my perspective, just handling abstract syntax trees, I just don't know. I just don't know what it is. I know it's a foreign type, something that doesn't come from my API, but I have no other information. And this is really, really a pain point when working that way. There are possible solutions. For instance, I could write my own path resolution algorithm. I could download each dependency on my own and parse it directly from crates.io. But this is just way too complex, and this is a very bad idea, since this is not our job. Our job is to take information and perform static analysis. Figuring out dependencies and import and path resolution is Rust C and Cargo job, and we do not want to do the same. I tried to do the same, and it really hurts. You do not want to do it, and this is why this whole talk is entitled Parsing Rust Code is Considered Harmful. You don't want to just parse Rust code, you want to do more than parsing. So, let's take our initial problem slide and add more requirements. So, we want to get information about a crate, but we do not want to rewrite a compiler and a dependency resolver. We want to be able to handle dependencies the easy way. Let's try to use the most simple approach, Rust C as a library. So we will try. The goal is to basically embed a custom version of Rust C in our executable and basically run as much of its code as possible, so that our cargo breaking contains only basically what it is supposed to contain, so breaking change detection. The idea, like this fits in a whole slide. This is a whole process of using Rust C as a library. Just add a nightly feature and you suddenly have access to everything, to the whole public API of the compiler, which is like easy. Just a custom feature to enable, and you suddenly have access to thousands of hours of engineering. This completely blew my mind. This is something which is already used by other people. For instance, Clippy, so the most common Rust linter, uses this technique for the simple reason that linting is actually static analysis performed in a specific way. So it makes sense to use similar method, right? Handling dependencies is complex. We need, when running the compiler, even if it's in a library, we need to tell it a lot of information about where to find all the dependencies of the crate we are currently compiling. My initial idea was to read the manifest file and just do what Cargo does, so computing a dependency graph, perform compilation of each crate separately, and then perform the final static analysis pass on the last crate. But this is, once again, too much work, and this is not the work we are supposed to do when doing static analysis. What we are supposed to do is to use cargo. It turns out cargo has a super nice environment variable, which is rustc wrapper, which allows us to tell to cargo that instead of using rustc, to invoke any custom binary. So we could tell it to invoke us instead. This works really well because our only job is to guess if we are actually building a dependency or the final crate. If we are building a dependency, then we just pull back on the actual rustc, perform the compilation. And if we are called for the very last invocation, the one where we are supposed to perform static analysis, then we can just perform static analysis, which is great. It's also very easy to interact with rustc when it's embedded as a library. There's a trait whose name is callbacks, and this is the whole entry point of the compiler. It allows to change the way, to customize the way the compiler is called. Maybe you want to tweak the settings. For instance, you may want to change the name of the crate as it's seen by rustc because you want to perform internal crimes, let's say. You may also want to change the abstract syntax tree that has been parsed. I don't know who wants it, but it could prove useful later. And, which is the most important part, it can also be used to perform MIR code analysis. Basically, MIR is a way a crate code and its dependencies are represented in rustc. At this step of the compilation, everything has been resolved, and we are almost guaranteed to have enough information so that we can perform all the static analysis we want. rustc is built using a very, not weird, not strange, but uncommon pattern when working, when writing Rust code. Basically, it's a whole query engine. The thing is that compiling a Rust program is kind of slow. Everyone in the room agrees, I'm pretty sure. So people wanted to make it complex. A simple way to make a complex program go faster is to ensure that no work is performed twice. This is the whole idea of this query engine. Basically, when doing static analysis, this way you are interacting with a struct whose name is tyctxt, which represents a typed context. And this is the structure you are going to perform queries against. This structure has a tremendous amount of method. It has about 500 methods and counting, which is like incredible. The problem with this approach, like we tried really hard to follow that way because it's the easiest way to get correct. It doesn't work. It's just too much. You are constantly tied to rustc. You can't even let data flow out of the callback traits, which I show earlier. You also need to spend a lot of time understanding how the compiler is written and how different pieces interact with each other, which is like very complex. This is a learning curve which is even steeper than the learning curve of Rust itself, in my opinion. About stability. This is not stable. This is the most unstable project I've never worked with. Basically, the thing is that the Rust compiler developers don't want to spend time stabilizing or keeping, like, not breaking their own internal APIs. It makes sense. They are focused on shipping a compiler, which is a very complex problem. They don't want to do any additional work, and it makes sense. But the result of this is that your project is going to break every once in a while because a developer somewhere decided to change the compiler internal. So let's update once again our slide. We don't want to be this tied to the compiler. We want something clean. We want to get data from the compiler and not constantly query information about the compiler. The most simple solution is to use rustdoc, and it kind of makes sense. When looking at, rustdoc is already a tool whose goal is to extract the API of a crate. So it has almost all the code required to perform this extraction step. The idea is that rustdoc has a custom flag whose name is output format, which allows us to tweak the way what files it will generate in the end. By default, it generates a bunch of HTML pages, but we can tell it to just do a JSON file. And this is great because a JSON file is easy to understand and to reason with. It outputs data in a specific format, using specific data structures defined in the compiler repository as rustdoc JSON types. And someone in the community is responsible for publishing regularly the rustdoc types traits, which basically maps to these data types. It uses CRD internally, so you just have to give it all the content of the JSON file generated by rustdoc, and it will do all its work on its own, which is perfect. We are freeing ourselves from the compiler. Right now, there is just invocating rustdoc, reading the JSON file, deserializing it, and then only static analysis, which is awesome. Also, it integrates perfectly with Cargo because you just can run Cargo rustdoc, and Cargo will figure out when to call rustc, when to call rustdoc, and you just have to read the final file, which is awesome. This is not perfect, though. It is limited to items. You cannot parse the content of a function body, which means that your project, in order for this approach to work, your project must be focused only on the public API and not what's inside functions, which may be a problem. Also, you only have information about a crate after macro are expanded, which may not be on the scope of your project. You may want to get actual pre-expansion, to perform pre-expansion analysis. This method is more stable than rustc, but still not that stable because the data type outputted by rustdoc may change without notice. But luckily for us, the release process of rustdoc types is almost automated, which means that fixing it is super easy. Okay, so these were all the approaches I had the opportunity to experiment with. They have upsides and downsides. For now, let's focus on something slightly different. Let's see if we can embed all these, let's see if we can imagine another approach which would fit, instead of fitting in a CI script or something, which we could run basically when the program is being written, so that we can lint indirect it at each keystroke that something is happening. Basically, in my opinion, the easiest way to do this would be to plug ourselves to Rust Analyzer, which is the most common Rust language integration used when developing. We could, for instance, spin a separate process which would communicate with Rust Analyzer. It doesn't have to be fancy code loading at runtime. We can just exchange a bunch of JSON files, JSON messages. And what's really interesting is that Rust Analyzer and the other language integrations are focused on performing as much computation as possible. This is the best way to give instant feedback when typing something. You want, for instance, your type checking to work instantaneously. So all Rust Analyzer is crafted so that as little recomputations are done. This means it has its own incremental and query-based computation models. And basically what it is doing is keeping track of the data required in order to compute another data. And each time the source data gets changed, then every data which depends from it will get recomputed, which is awesome because all the static analysis we may perform wraps kind of well in this data flow, and I need this in order to do that, and very functional, as in a per function. So one way we could do that would be to be able to communicate with Rust Analyzer and telling it what are the queries we want to perform, and it will, for instance, build the same data dependency tree for our tool. This way, it would allow us to recompute, to perform the static analysis only when required, only on what we require, and perform, like, do it almost instantly, which is what you want, once again, when you want to plug yourself in an idea. Okay, so that's the end of my talk. Thank you so much for listening.